Welcome to our Lecture 8, where we'll look at doing multiple Poisson regression, and it'll be a logical extension from what we did with simple Poisson regression. We'll look at this using R. And again, we're going to use some data that actually is part of R if you load the proper library, and so all of you back in the first term actually use the install packages tool to add the spatial epi library to your R library in your hard drive. And what we're going to do now is actually bring this into our session by using the library function and pulling this book off the shelf essentially and putting it on our desktop now, and that's what the library function does. So add library spatial epi to this session and you'll be good to go. We're going to be working with our Penn lung cancer data, the Pennsylvania lung cancer data set, just like we did in the our lecture on simple Poisson regression. So we're going to look at this, we're going to load this from the spatial epi library using that data command, and then look at what's in it. And this is an object that has multiple pieces to it. So if we just again look at the class of Penn LC, it's a list and it includes a compilation of different objects in one object, uber object called list. We're going to look at the object called data. That's actually a data frame containing the data we use to do these analyses. So I'm going to take and pull off the Penn LC $data. That'll pull off the data frame. I'm going to store it in a data frame called PLC. So the class of PLC again is. So I'm doing a review here just because it's been a while since we did this simple Poisson regression video. Look at the names in here, and we have county, cases, population, race, gender, and age. So let's look at sex to start, and we'll just do a couple simple Poisson regressions like we did before to refresh your memory. We look at the class of what's called gender. In these data, it's a factor, and it's stored as an M or an F, male or female. And the corresponding numeric versions of these two things are 2 for male and 1 for female. I did a table of the ASDAT numeric version of the factor class variable PLC $gender. Another thing we're going to need to do, and we may recall from the last session on simple Poisson regression, but it turns out there is one county sex, age, race subgroup in these data where there's nobody in that population. There's one county in a particular combination of sex, age, and race where there's nobody in the county who fits those 3 criteria, and it has a value of 0. And because all the Poisson computations are done on the log scale, having a 0, even though the algorithm is going to aggregate it across these different sex, age, and race groups, depending on what our predictor set is, it will cause an error. So a little tweak that I've done, and this is very common when you have 0 cells with 0 observations in population count data, and the population serving as the denominator in some situations, so we can't divide by 0, and things would be done on the log scale where we can't have zeros as well. This is to replace the situation where the population count is 0 with a 1. Just give it a small value. It's not going to affect our overall results, but it's going to allow the algorithm to run. So what I did here was replace PLC, the column population. I used the if-else option and said if, remember this works, it says you put a condition in and say if this condition, do the second thing in the command, else do the third thing in the command. So I said if else PLC population is equal to 0, replace that with a 1, and if it's not equal to 0, just keep it as is. So there's only one situation where we have a 0 in these data, and this will just replace it as a 1. The other thing I did, just to make it easier for my interpreter purposes, and you don't have to, but I like to create 1, 0 options for my factor variables sometimes. Sometimes it makes it easier for me to work with them in a regression context, although it would be fine to keep it as a factor as well. But I'm just going to do that for my own preferences. So I'm going to create a vector called female, which is equal to 2 minus ASDAT numeric version of sex. So just remember gender here, which represents biological sex. The values were M and F, and the ASDAT numeric values, or the numeric values of those factor counterparts, was M's or males were 2s and females were 1s. So I'm going to create a new column called female, which is a numeric variable, which takes on a value of 2 minus the numeric analog or counterpart to those gender factor levels. So if the person is male, their numeric value of the PLC gender factor is 2, and so their value of female is 2 minus 2 or 0. If the person was female, the as.numeric version of their factored gender variable was 1, and so PLC female equals 2 minus 1 or 1 for this group. So now let's look at a simple Poisson regression with female as a predictor, just to refresh our memory on how to do this. We're going to use the GLM command again. Our outcome is the total number of cases in each combination of sex, age, and race classification for each county. Our predictor here is female. We have to put in the offset of log of the population. That's, in other words, putting in the denominator for those rates, and we talked about the reason for doing that, or why the computer expects it this way back when we did simple Poisson regression. Our family is Poisson, and we're linking our outcome, the rate, to the predictors on the log scale, and we're using the PLC data set. Just look at what we did here. Okay. Oh, and I forgot, as I always do, to run the command I just told you about. Now we have female. And let's just do this summary. SPR1, there we go. And so we get an intercept here of negative 6.95 and a slope for female of negative 0.28. Let me just show you what would happen if we ran it the other way using the factored version of sex. So I'm going to rerun this and put in gender here. We get the same result, except it would be in the direction comparing males to females, because the factor coding was such that males were the larger value. So if we do SPR1B here, so you can see we get a different intercept because now the reference group is females and not males like it was in this previous setup. But notice the slopes are identical in absolute value, just opposite signs. So certainly you could have done it that way as well and gotten the same overall result. We get the same predicted rates for both males and females regardless of how we did this. Let's go on and look at age. This was only available in categories in these data. Let me just show you a table again to remind you of what they called age. And so the first group was 40 to 59 years old, the second group was 60 to 69 years old, the third group was 70 and older, and the fourth group was under 40. I wanted to set this up. There's no reason we couldn't do the regression with the categories as such, but what it's going to do in the factor world, these are factors, and it will take the one with the lowest numeric value. So let me just run that as .numeric. PLC age, and of course it helps to spell it correctly, as do not numeric. So the lowest value here in order, and it's just is that the 40 to 59-year-old group was coded 1, 60 to 69 group, the underlying numerical version of this was 2. And so when we run this, the default is to take the lowest value on the numeric version as the reference group. So if we had run it as is, the reference group for the age comparisons was 40 to 59 years old. I thought it would be more logical to make this a truly ascending comparison, so I wanted to recode or create a new version of age so that the reference group was less than 40. And we did this in the simple Poisson regression lecture as well, the R lecture for that, but let me just remind you. So I created a new variable called AgeCat. I'm going to add it as a column to my PLC data frame. I'm going to invoke the if-else command again. And in this old schema, the numeric counterpart to the factor version of under 40 was 4. So in this, I'm going to say if-else, so give it a condition. If the as.numeric version of PLC age is equal to 4, if that's true, replace it with a 1. And otherwise, the else part is take the current numeric version and add 1. So I'm going to take those who are under 40, who are formerly called 4, or their numeric counterpart to their factor variable was 4. I'm going to create a new variable where they're now 1s. And those that were previously 1, 2, 3, or 4 are now going to be 2, 3, and 4 respectively. So I'm just shifting things around so that my comparison group now is the under 40 group. And in situations where this will not be a factor variable, it would be an integer variable, but when I turn it or use it as a factor, it will take the lowest value as the reference. So that group that is now on the numeric scale of 1 is the under 40 group. So if I do this and then I run this, I get the results. I have to put as.factor agecat because the class of that variable I created, the 1, 2, 3, or 4 was numeric, and so if I just put that in, it would treat it as a continuous predictor 1, 2, 3, or 4. So to keep these as categorical, I use the as.factor version in this command, and we can see I get the intercept plus the slopes for the 3 subsequent age categories. And again, we get that result that anybody over 40 has a much higher risk than those who were less than 40 of being diagnosed with lung cancer. So now I have a situation where I have a single model, single predictor, and something we didn't talk about when we first introduced simple regression models, but now we'll bring it back in the context because we've talked about it in the multiple regression context. But let's just think about the setup. So technically speaking, if I want to ask if age is a statistically significant predictor of lung cancer, to do this formally, now we know when we look at some of those specific comparisons of each non-reference group to the reference, they're all statistically different from the reference. So we know it is a statistically, at least some differences are statistically significant, and hence age is associated with the outcome on the whole. But for reasons that we talked about in the lectures, we could miss that if the comparison specified by the way we modeled our categorical predictor, none of those were significant, whereas some of the other ones not explicitly represented by the modeling were. So just to set this up, I just want to say we can test this. That the model we have is the log of the incidence rate of lung cancer is equal to an intercept plus slopes for each of our 3 indicators of the non-reference age groups. And we have p-values in that output, and we have confidence intervals for each of these slopes individually. And the p-values each test the null hypothesis that the respective slope on its own is equal to 0 in a model with the other slopes. But it only is asking about that particular slope. And for reasons we spoke of, if we want to be totally thorough in the comparisons we make, in order to test for all possible age-specific comparisons, we'd have to be more global and test all 3 slopes at once together, R0. Now, the way we talked about doing this in the multiple regression context was by specifying an extended model and a null model. But we can think of this is technically, in the way I've defined simple regressions, a simple regression, despite the fact that it has more than one x. I call it a simple regression because there's only one predictor, age. But we can think of this as our extended model, and if we want it to test against a null model, the null model would simply be a model where there were no predictors. And so if we wanted to formally test whether age, as modeled in 4 categories, was a statistically significant correlate or predictor of lung cancer, we could test it against a model that didn't have age, but because the only predictor in our model here is age, the model without age would only have an intercept. But we could do a likelihood ratio test in the same manner we've talked about for any of our comparisons by specifying the null model as the one with just an intercept. So let's look at doing this. So I'm going to set up what I call a null model here. I'm going to run this command here. I'm going to run the GLM command, and I'm going to include no predictors. I'm just going to include my offset for the log of population. So the implication here is that this is what they call an intercept-only model. This assumes the same and estimates a common log incidence rate for everybody, regardless of any of their characteristics. So I'm going to fit that and store it in an object called null. Then I'm going to pull up this library we've used before so that we can run these likelihood ratio tests. I'm going to add this to my actual session library here, this thing called LM test. So we can do the test, and then the command we have was LR test, where we put in, we list in order. The first argument would be the null model, and the second argument would be the extended And so I'm going to do that in this setup here, and I called the null model null here. If I do this, I get a comparison that compares model 2, where we have age category plus an offset, to model 1, where we just have an offset. So just to be clear, the estimated intercepts for these two models are not going to be the same because they're different models. So if we do a summary of the null model, the estimated intercept here is negative 7.085. When we had done it with age category in there, the estimated intercept was negative 11.58. That's because they're estimating different, the log incidence for different groups. In the null model, where we just have an intercept, it's the log incidence rate for everyone, regardless of their age. In the model where we have age group as the predictor, then it's the log incidence rate for the under 40 group, the reference group. So those intercepts are not necessarily the same, but we're testing the one that has the extended model, where they have the an intercept estimate for that model and 3 slopes versus the null. And again, if we do this LR test, the chances of getting the p-value for this is smaller than 2.2 times 10 to the negative 16. So we would reject the null model in favor of the extended model and conclude that age in those 4 categories is statistically associated with lung cancer. Finally, we looked at race. Race is coded unimaginably as white or non-white. This is the simple Poisson regression for that. Results from that are SPR3. The race W means, so let's just look at the table of race. White and other is what they call it, white and non-white. That's the classification in these data. It doesn't come in any finer classifications than that. And so in the numeric version of these, white is coded as 2, other is 1, so other will be the reference group in these comparisons, and that's why it says race W here. And so this is the unadjusted association between lung cancer and race across all these counties in Pennsylvania. So now we can start doing things like multiple Poisson regressions, and it's easy to do. We just include more predictors in our GLM command. So if I wanted to do a lung cancer on sex and age, I could do MPR2, we could call it whatever you want. I'm going to assign that the output. I'm going to create an object that stores the outputted object, the GLM command. For cases, we've got the age cat, as.factor age cat. We've got female. For sex, we have the offset of the log population. Again, family equals Poisson, link equals log, data equals PLC. If we do this, we get this resulting multiple Poisson regression model. If we look at a summary of it, we get an intercept, we get the slopes for our age coefficients and the slope for females compared to males, adjusting for age. If we wanted these on the incidence rate ratio scale, we could exponentiate the coefficients here. So we could use exponentiate the return vector we get from applying the coef function to this multiple Poisson regression. And that would give us the exponentiated intercept and the exponentiated slopes. In other words, the incidence rate ratios for each of these. We can also get confidence intervals by for the incidence rate described by the intercept and the incidence rate ratios described by the slope by exponentiating the output of the conf command applied to this object. So if we wanted to test whether age was a statistically significant predictor above and beyond what is predicted by sex, the model we have here has sex and age. The null model for this would be the model which only had sex as a predictor, which we called SPR1. We stored the results of that in our object called SPR1. So I could do a likelihood ratio test of this multiple Poisson model that includes sex and age against this simple Poisson model that only includes sex and see what the results look like. And here we get, again, a very small p-value. And this is stated as default lower bound. It's not that we're getting the same p-value each time, 2.2 times 10 to the negative 16. It's just when it comes in lower than that, it just puts that as the bound on that. So I promise you, we're not getting the same results each time, but every case the p-value is very small, and that's its bounded cutoff. I could go ahead and do this one more time and add in race on top of things and do the multiple Poisson regression that includes age in 4 categories, sex, and race, and this is how I ultimately got the results for the lecture results presented. But now I could do a likelihood ratio test of this model to the model that includes only sex and age to see if race was a statistically significant predictor of lung cancer above and beyond age and sex. We can already, since race only takes on one X, we can look at the beta, we can look at the p-value for its coefficient or its slope here and see that that's the case. But just for the exercise here, I will do it as we could get the same comparison by comparing this model to the one without race. And again, we're going to get the p-value is slightly different, but in both cases, because it's a slightly different test, but in both cases, they're very, 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 very small. So hopefully you can see how easy it is to extend the idea of simple Poisson regression to multiple Poisson regression in our context. And this gives some more insight in how to do those null and extended model comparisons using R.